let's dive into CGA. Who in the audience has no experience in writing CGA code whatsoever? That's cool. Who would say is pretty advanced? Nice. All right. So my little workshop here is showing a couple of little neat tricks of things that I have used many times over the years, but are not necessarily directly written in a documentation. And what's cool about those little details is it shows you how to work with the quote-unquote limitations of the language, and how to become a little bit more creative in using certain basic fundamentals to your advantage. And so with that, I prepared a couple of examples. Let's see how fast we can go through them, and I hope that you learn something. Let's dive in. All right. So what we see here is basically a sloped, let's say a parcel, a sloped polygon. And in urban planning, it's actually very common that you are interested in the projected area of this polygon. And so let's go in and open the console. And let's work on this rule here. All right. So the grid size here is 10 meters. So the polygon that we have is 100 square meters. Cool. So the magic number is 100 that we're interested in. But if we are going to the CGA reference, and we are going, for example, to the geometry function, where are you? Geometry.area, then we see that we have, it's actually working with certain selectors, and those are the typical ones that you also may know from the component split. So these things are back, bottom, front, object.front, world.north, and so on. But these are the selectors that are looking at in these directions of the scope orientations of the polygons that match this direction. But in this case here, we are actually limited because with these selectors, you just can, no matter how you look at this one polygon, you can just get the area of the polygon itself using this, the function geometry.area. So, but what we are interested in is the projected area. So let's go in this direction and shape and just print geometry. Geometry.area. All right, and we are going to assign the rule. Bam, and we see that indeed it is bigger than 100. So if we're making it more and more extreme, the further down we go, right? So that's cool. Now, how do we fix this? Because we're interested in without editing this polygon, without splitting it or rotating it, because we don't want to mess with it. That's the input data. So what we can do here is we can say extrude, and then go to world up flat top, And then the distance is scope.sy, the vertical distance. But for that, we need to make sure that the scope is actually whirled up. So here we can say align scope to axis y. I'm not going to go too far into the details of the scope orientation. That's what you have the reworked CGA tutorials for, right? All right. So now what this construction is doing is it will create this flat top with an extrusion height of the vertical height in world height with this geometry. Now the fun thing is, with this we have one of those polygons is actually the area that we're interested in, right? So what we can say here is, for example, let's shorten it, and here we can say let's make it nice and clean. Top. And this will give you, let's generate again, exactly 100, right? So you can store this as an attribute. And then another little joke here is if you're going to a component split and you use the face index 0, let's say shape, you are back at the original polygon, because the convention of the extrude operation is that the original face will remain index 0, so you can go back to the original. And that's a neat little tip. Who didn't know this one? Okay, that's good already. Good enough. Cool. Tip number 2. Yeah. So that's the shape L. Let's go here, move it up a notch. Tip number 2. All right. When we are analyzing this shape here, we see that the first step, for those that don't see it very well, the first step is here. It's indicated slightly orange, right? So vertex 0, vertex 1. And this first edge defines where is front of this polygon. So when we say we would like to split this with as an L, with the code that we have here, the operation shape L, we're going to split 3 meters and 3 meters as an L. This will result in the geometry that we just saw here. That's interesting. Tip 2, that's the wrong one. Now it's correct, because we didn't have colors yet. Right, so the L is from the left side and from the front. Cool, so that's simple enough. Now, if we are going to make this one a little bit more complicated, we are going to eliminate shape L and we're going to switch to a shape O, which is basically can replicate the shape L also, because the other 2 dimensions of the O are just 0. So what you can do here is you can say dimension, 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 and then if you regenerate it like that, you will obviously get the full O form here, right? Now, very often you are writing code in urban planning, for example, where you would like to randomize things and make them a little bit more interesting. And so for these things, what you very often have is constructs like rand of offsets between 2 and 4 meters, for example, right? That's not going to work because now this is an attribute. It's going to stay the same value. And let me actually colorize this one here. So you can see that it's randomizing the dimensions on all ends. But sometimes you would like to actually have still a shape L, right? But going in and have percentages of where you're using a shape L, where you are using a shape O, and what the orientation is, that's cumbersome. So a very cool and neat little trick is just to use probabilities in this function here. So here you can say 20%, it's actually the dimension is going to be 0, so it's not going to cut, and anything else, oops, is going to actually do the cut. So if you generate like that, you have a very neat little construction where you have very short code and a lot of variation visually. All right. Tip number 2. Nice one. All right. Then tip number 3 is also something that is very little known, but has been around for ages. Here we have the code for rule A and B. Oh, go on over. All right. In rule A, we are importing rule B. And we are going to name this one rule B. And let's move to the next shape, to this guy here. And assign rule B first. So here we can say shape. And we say, for example, color. 1, 0, 0. So what the rule B is doing, if I drag and drop it, it's gonna colorize red, right? Now, if I have another start rule here, in rule, when I'm going to call B dot shape, and I'm assigning rule A, it will do the same thing, right? This one is imported. Let's change this to yellow. Importing rules, pretty straightforward, right? And in the model hierarchy, you know that all the shapes are always in kind of in this tree in the hierarchy going down, 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 and you split them so the tree becomes bigger. Now, the cool thing here is what you can do is the following. Here you can say something like, this is the result. And you save it exactly like this, and you get this little warning error here that says it's an undefined rule. yeah, that's correct, because it's not defined. And very typically, to either stop a rule or to suppress this warning, what you can do is, or what you typically do is you put the point there, right? But in this case here, we are going to leave it like that, and we're going to the master rule, and then we're going to do this, b.result, and we are going to make it like that. That's a pretty cool little thing, because the geometry that you defined in the import, you're actually looping it back up to the master rule. And you can do the same thing also with attributes and bringing the attributes back up. That's something that is sometimes super handy. Cool. Sweet. Oh, that's this one. Let's go to this one first. The others might take a little bit longer. All right. All right. So when you're writing your CGA code, it's very common that you would actually like to visualize the orientation of the scope. Now, typically, this is done when you go to Window, Model Hierarchy, then you say Inspect Model, and you click on the model. And then by default, up there on the right side here, you see that the scope of the selected CGA shape is visualized. This will actually show you the orange cube with the x-axis, which is red, the y-axis that is green, and the z-axis that is blue. But this is sometimes a little bit uncomfy, so we would like to construct this as geometry. One cool little thing, and that's what I'm going to show you here, is the following. So first, in this geometry, we would like to have the box first. Super simple. Primitive cube. This is going to replace the current shape, the input shape which we have here. It's a three-dimensional shape. It's not a footprint, but same principle. And we are going to replace this geometry. Let me put an X here. Hello. Can I get out here? Yeah. All right. With a geometry. New keyboard. And now the thing is, primitive cube, the topology of the geometry that is inserted here is always going to be the same. So the orientation of the edges will remain constant. So we can build on that, and we can say here we are going to create a component split of the edges, and we are going to peek at the notes. Number 12 should be the X edge that we saw before. Now a little construction here. We are going to insert the geometry. Let's say dimension is, let's say, 0.5. Dimension. Center YZ. Primitive cube color 100 x. Bam. It's the same, basically the same line we had before, right? Now we're gonna copy paste the whole thingy a couple of times. Same for Y and Z. Z's gonna be blue. Oops. And Y. And the according indices are, what was it, 3, 3 and 11. And there you have your scope visualizer that you can copy paste to all of your rules. Also pretty neat. Cool. Which one do we choose next? Let's use this one. All right. Hello. 1, 2, 3, 4. This geometry here. All right, let's have a look at the geometry first. The bottom edge here is the first edge. All right. So the problem I would like to solve here is the following. I would like to cut this shape many times until or as long, let's say it's a little bit a special case of an example, but just to show you how to work through it. So I want to start cutting from this side, cutting until or as long as the remaining piece of the the remainder becomes a polygon that has 4 points. So at the moment you see it has 5 points, and so when I start cutting at the point where it becomes the rest up here that actually just has 4 points, then I want to stop cutting. And then I'm interested in how many cuts did it take to get there. It's a little bit a random example, but let's look into how you would code this. So first of all, we want to define an attribute. That's, let's say, the delta. That's how far do you split. And let's say 0.25 meters. Then you can say attribute number of steps we are taking, so that's 0 at the beginning. Then we are going to go into a recursion because we want to do things in a loop. And here we are going to say case n vertices is bigger, is bigger than 4. Set number of steps to number of steps plus 1. And we are actually going to make a cut. So that's going to be split in the Z direction, delta, and then we are going to say nil. And the rest we're going back into the recursion. So the structure here is same. That's the test, right? Keep cutting and keep increasing the steps until the geometry has 4 points. And then once you are there, do something different. And let's stop at this point. So let's assign the rule. And actually quickly visualize the geometry. So these are the steps, these are the cuts that are made, right? But let's assume now we would like to, instead of having all of these individual cuts afterwards, we would like to have them combined into one cut. But we didn't know how far we have to cut. And this is where this really cool operation comes in called reset geometry. So we're going to go here with nil. And we're going to, at the end, go and do exactly the same thing. Oops. Just with the resulting number of steps multiplied by the delta. And this is the rest here. Sorry?
It reminds me of the sketch of divide tool that you can see where it's cutting before you cut it. So
yeah, it kind of goes in that direction. Now, reset geometry resets the whole thing to the original shape. I wish there were more options to that, where you can say at a specific branch, go back up to that tagged branch. Because here you have to you're cutting, memorizing, and then you're going all the way back. But there's so many constructions where you could technically test certain things or find certain things out, but then you don't want to. This might be just on a small part of the building where you're testing, then falling back with the information that you just gathered, and then go back. So this could be reset geometry to certain states in the model hierarchy that are tagged, reset back to those, would be really cool. It's probably a pain in the ass to implement, but yeah. Backlog 1 million. Right? Does the construct make sense? Maybe it's helpful, and yeah. I mean, obviously, the more precise you want to go, the smaller you can do the delta, right? Yeah, that was number 5th actually. And now we're going to do one more. Where?
Can you do that in the time steps? Like each section, sorry, it's probably very special. Like for each section to happen at a certain time every second, for example. Like a sort of animation.
So the question was if this could be animated over time. I believe this would be possible with Python and feeding in certain attribute changes that are timed. But yeah, I believe this would be possible. So you need to construct a little bit the attribute transfer for our setting from Python to inform the model generation. But yeah, technically this should work. All right, I just lost the 5th rule. Go over here. Cool. Now that's going to be a funky one. You're going to love it. All right, we are defining an array. An array is basically a list. And it's going to be of the type float. And we say we have a couple of values in here that are 1, 1, 1, 3, 2, 2, 2. And we're going to go and assign it to this guy here. And you see the list, which has obviously seven entries. Cool. Now, there may be cases where you would like to find some information in that array, but the function isn't available by default. So something like, what is the max value of the array? There are many constructs you could think of, or what is the mean value of what you have in the array, or whatever it is, right? So, and a lot of those cases are not possible to have as official functions directly in CGA, because you could go anywhere. So now the question is, how would we process arrays and find out more about them? Or find, for example, the maximum value ourselves. So let's go there. What we can do here is find biggest value in array, and then we give it the name A. Now we are going to so-called, I believe this is called overloading. The function, we're going to go in scary territory here. Functions are already complex to beginners, but now we are actually using recursive functions. So we are going to basically loop over, or using a function, loop over all of the elements that are in the array. So what we're doing here is we're just using the same name here. We're feeding the same original information into a new function, and we say, okay, we are passing on an index, which element we are processing. And then, because we're interested in the biggest value, the maximum value, we're going to start with an extremely low value that is probably smaller than anything we will ever touch. And we're going to define this function here. And we are going to say A stays A. This one becomes an index, and this one becomes, what did we say here? The, let's say, biggest value. Cool. Now, what we can say, because we are looping now, or we are going to be looping by calling the same function again, we can say case n is the size of A. We have tested every single part or every single element of the list, and if we have reached the size, so that was the number of 7, if you have the 7th, the length of the array, that means we have gone through the whole array, so we can stop. So then we are actually returning the biggest value to this function up here, which we are calling down here. Let's go here. And we're feeding in array, right? So it's a little bit inception. Cool, but then we can also say okay, if we are not yet done, we do something different. And now we're basically testing the current value in the list that we're testing. Is it bigger than the biggest value we have so far? Yes or no? Right. So here we can say case, the array at the location n, which of those indices, starting at 0, if this one is bigger than the biggest current value that we have, then we're going back into the recursion and test the next element. And that's going to be basically going here to the next element. That means n plus 1. And we are going to define the new biggest one as the current one. Else, oops, we're going to go to the next one. And we're not going to change the biggest that was already happening, but we're defining it again. And now if we generate this, the result that is printed down is actually the value 3, which corresponds to the biggest value in the whole array. Constructs like these, especially with sorting through lists and different types of data, are quite common if you're going further and further with more and more complex constructions in CGA. These were hopefully a couple of cool tips you may use, and yeah, so I hope you learned something. Thanks a lot. By the way, if those that are interested in the code, the examples themselves, send me an email and I can send it to everybody. If there are some questions, then you can. There's the mic. Otherwise, we can go to lunch.
This is great to see the master at work. I was just wondering about the when you started with the first one, the slanted box. I started thinking about height control plane, and on the urban side, it's driven by the regulatory model. So you're putting in the ratios of what you're building to, but the on-the-fly occlusion has always eluded me. So I don't know if you're taking special requests, but I would like to see some more possibilities with how you can have that height control plane and move the building around and see that occlusion and see the color flagged on there to get the values back in the print function. So we can talk later.
I do believe I think I know which where you're going. So basically, the urban planning regulations dictate certain sky planes, or let's say a volume or geometric constraints.
Yeah.
And what you would like to have is, for example, if there's a plane here, you would like to be moving the footprint around and then actually see how high you can build. And this is definitely something that the most direct approach at the moment, you mentioned it, the occlusions, is just kind of build floor by floor by floor by floor, and in recursions, and checking the last floor against the occlusion ghost, as they're called, or if it occludes with the sky plane. Yeah, I mean the occlusion queries there are sometimes a bit tricky and finicky, but I assume you have been working with those already.
Yeah, I went from getting the really sliver floors at the top to at least getting it to fix with that.
Yeah.
But I still have trouble of being able to move it around and it to be as expected. So it's probably just a user error there, but
maybe, yeah. But if you would like to, if you're interested, we can have a look at that.
That's a dream come true.
Yep.
Thank you.
Yep. More questions? No, everybody hungry?
I have one.
Oh, you have one?
Yeah.
Wee.
Probably hard to answer, but for everything that you've just shown, all these tips and tricks, relating it back to an urban planning, urban design use case, can you do that for each one in a sentence?
Yes. No. Yes. So projected area. That's something that is quite common. I think that one was pretty intuitive. Right. Regarding, you have. It's just certain planning regulations just work with projected areas, and you somehow need to get to these geometric values. So that's a pretty straightforward one. Then tip 2 was with the random cuts from different sides. That one is something that when you are working on master plans is something that it's very often that you're kind of, you want to have a certain controlled randomization where you're placing, let's say, the simplest example that comes to mind that is super intuitive is American suburbs, where you have the plots that all look very similar in the shape-wise or form-wise, but then you would like to place the building once in the back, once in the front. Sometimes it's a little bit bigger, sometimes, and in rare occasions, there's no building there whatsoever. So working with probabilities and as short code or as little code as possible, but still kind of being able to control the distribution of the masses is something where these little combinations of functions to eliminate certain cases that you have. That's where this one comes in, for example. And then the tip 3 was the one with the looping the values back up to the master rule. That is something where you have, especially in larger amounts of code, where for example one CGA file is longer than 500 or 1,000 lines of code, it becomes really hard to maintain it because you're tracking so many different things, and they're breaking up rules into certain things. Like one rule is just distributing or just cutting open space, parks, and is in general just cutting up the plots, the parcels. But then from there you are going into another rule, into obviously an imported rule that goes to the next problem of, okay, now we're working on the plots. Now we're going to distribute the buildings on these plots, and we have certain parts where we know it's gonna be garden or open space or things like that. But then that in itself might be another rule that is just doing gardens and open spaces, like distributing trees and things like that. And because you may have multiple entry points of, maybe you want to have a rule that only specifically places, let's say, a park on a specific shape. So you want to have this as a standalone rule, but also as a part of a bigger conglomerate of an import structure of multiple rules. And so for that, bringing certain pieces of the result from imported rules back up to the master rule, from where you can redistribute it otherwise is sometimes super helpful. Then That was done one. Then the recursive cut, where you're cutting, testing, and then when you have the information, you go back and cut once. That's maybe a little bit more of a, that was more of an example of the thinking and working with the limitations of the tool or of any programming language for that matter. But there are many of these cases where you have a certain optimization task at hand where you want to geometrically test multiple things before you decide which one is the best one. There are more complex constructs that you can do together with reporting and then using Python to analyze the reports and then pick the best seed that you had at the beginning and go and set this one. But that is a little bit further or a little bit more complex. And another really interesting, let's say, different approach of that was also, for example, the area split, which was introduced by the developers a couple of years back. When you have a shape L and you have to do one cut, but you do with a certain target area. But if in the L, let's say the L, if the L is this big, if a certain target area is here, it can cut nicely, but there's this jump in area suddenly that if you're below or before the cut or after the cut, it's pretty much impossible to see how far would you have to cut to reach that target area. So the split area is kind of also doing some of this testing already built in one operation. But there are certain scenarios where were even using some like shape area or the area split doesn't help you because you need to implement a different logic. So that's more problem-solving methodology that I showcased here. But it definitely has applications for urban planning. Scope visualization, anyway, this is kind of for debugging purposes, and then finding the biggest value in an array could be whatever data processing for urban metadata which you have in, or like, I don't know, if you have, for example, an array that would encode coming from GIS, the neighboring buildings, how high are they? And where are they located? So you could inform your building with some neighboring metadata, and then you have these as lists or as arrays of metadata, and then say, okay, we can, if the building is next to a high-rise building, then, I don't know, make it red, otherwise make it blue. And so that would be kind of being code-based analysis of metadata that is given. Just one example.
Thanks.
That was more than one sentence each. Sorry. All right, thanks.